Good morning, everyone. So we have the lecture quiz open today. I'll have it on another slide, a couple slides from now for those that are just coming in. I just wanted to start with a couple announcements this morning. We do have midterm 1 taking place next Tuesday during recitations. So just a few exam preparation tips to give you guys a few ideas how to start thinking about that upcoming exam. One is that the study cycle is important. Those of you guys that are here in lecture, that's part of it, is coming to class or watching videos, trying to keep up with like either those tutorials or coming to class is really the first step. Taking notes, kind of trying to figure out what doesn't make sense so you can go do more work after class in terms of either reading or finding problems, finding examples, asking questions. Using AI will help too for some of your problems. So you can go try to read either the covered sections in the textbook, or you can try to spot read the topics that are most confusing to you. If everything's confusing, I usually go back to square one and try to start moving forward. Try to work simpler examples first. That's where those post-lecture problem sets come into play, is that those are really designed to give you like an introductory level, like really basic questions to try to then lead you towards, more exam level problems. Our exams really don't have the hardest of problems. They might have a couple questions that are challenging, but overall, they're gonna have a lot of questions that look like those post-lecture problems, those in-chapter examples, those sample exam exercises that you see in the textbook and in those post-lecture assignments. So just you can also try to reread your notes at times. You can try to rewatch lecture videos if that's helpful. You can try to revisit earlier concepts if you get stuck on something. Visit office hours, use AI when you're stuck on a concept. Has anybody ever just said, teach me a concept with like AI? Has anybody ever tried that out? Has anybody ever said, give me a review of a topic with AI or explain something to you? Has anybody ever tried to make a quiz with AI? I see the same hand going up, love that. But AI is awesome. Like you can go to Google Gemini or ChatGPT or whatever, Copilot probably does this too. You can say, make me a quiz over significant figures. And I did this on Gemini, and the quiz that popped up was really basic. It was like, how many sig figs are in this number? What's the addition result? What's the subtraction result? Really basic questions up front. And then I did the 10 questions, got a pretty good score. Then it asked me, do you want another quiz? And if so, do you want it to be harder? And so you can start with a topic, like give me a quiz on nomenclature. We're about to get into that. You can even say from the perspective of our textbook, Chemistry Essential Science, we're on the 15th edition. Google Gemini seemed to know exactly what the book was. I even told it, write me a practice quiz over chapter 1 of that book, and it gave me a set of 10 questions that were reflective of our chapter 1. So you can use self-assessment along the way. Like you can use my daily quizzes. If you haven't seen this, if you go to the lecture videos tab or the lectures module, underneath that module is a daily quiz module. Just a bunch of PDF quizzes. There's some video solutions to those quizzes too. There's links at the bottom of that page that have some video solutions. I think all of the chapter 1 through 3 quizzes have solution videos. Then it kind of is more like every other quiz or so afterwards. So you can use AI, like I said, to create quizzes too. My recommendation for AI is try to tell it what book you're using, because that'll narrow in its quiz questions for you. Google Gemini, in my opinion, works the best because it's like a free version of ChatGPT and it's a little bit more powerful than Copilot in terms of things that you have more freely available. How many of you guys are still paying for chat? I asked this earlier before. Anybody paying that subscription fee to use ChatGPT? A few hands. I think it's kind of not necessarily worth the money, especially if you can just use something like Gemini that OSU now provides. We'll put some practice exams up soon over the next day or so that you can use, but these are necessarily not a great starting point for studying. They're kind of a better ending point for studying. Once you feel like you've kind of prepared across chapters 1 and 2, we haven't even completed our coverage of chapter 2 yet. Once we're finished covering chapter 2 and you've kind of finished going over some homework sets, some simple problems and some examples, then I think you can start thinking, can we take a practice test, see how we do? A practice test to me is a good reflection of how the real exam might go. If you take the practice exam and get like an 11 out of 20, the real exam might be headed for that score if we don't kind of revisit those concepts more largely and in general. If we just specifically look at the questions on the practice exam, they're not from a wide enough variety of problems to give us a good sample of what we need to know for the real exam. So don't treat the practice exams like a study guide. They're just a snapshot of 20 questions that were good to ask. Usually in some past semester. Usually you're just getting an old midterm. It's not going to encompass the hundreds of examples you might get that you might have your questions pulled from for your exam. So the better place to start with is reading the chapter, looking at your notes, looking at those simple examples, understanding those, and then just treating the practice exam like a quick snapshot to see how you might do in the real exam. And I think we put 2 up, maybe 3, so that you can take one, do some more studying, take another, and hopefully go from that. If you got the 11 out of 20, maybe you do some review, and the second time you take the test, you get a 17 out of 20 on the next one on a different set of questions, and you have more confidence heading into the real exam. Some of these topics are a little bit simple. If you've been sitting in class going, I've kind of seen all this before, this really isn't that hard, you take practice exams or doing well, that's great. Just remember, we might hit a chapter or a topic as we go that is more confusing. You might have to do more of that, like digging into the book, reading examples, reading through the book, doing examples to understand those concepts. So just know if everything's coming to you really easy so far, we may hit a point where you have to really buckle down and do some more of that legwork in terms of the study cycle, doing some practice problems, some self-assessment, etc. If you need help, drop by my office hours. They're listed here below. If you need to find these outside of class sometime later in the semester, just go to the contacts page in Carmen. There's a link right on the main page. But today they're 10 to 11:15, Fridays 9 a.m. after class till 10:30, and then Monday afternoons. So just drop by if you have questions. Okay, the Amgen Study Center, we mentioned this in the first lecture, has changed some of their hours and updated them. So their hours now are Monday to Friday, 4 to 8 p.m., and Sunday, 3 to 5. And that is drop-in tutoring. That's when they have some hours, I believe, that they have staff present that can take questions, that can help you out with your studying and some of your concepts, specifically for the courses that are listed. So they should have people present that are able to help with those areas. And then they have these additional hours over here where they're just generally open, where you can drop in and study, and at least other people could be in the room, students, but not necessarily tutors or helpers. So there's some quiet space rooms available too. So this is posted, if you want to get this slide, this is in the lecture slides as a PDF, so you can find it there at the very bottom, like with the announcements tab where the lecture videos appear. Okay, let me put this up again for anybody who's come in since this was up at the start of class. Oh, sorry, one. Okay, so let's talk a little bit about nomenclature. So that's kind of the rest of chapter 2 is on the concept of naming compounds, so we can kind of get the language of formulas that we can give you so you can understand what the compound is. We want to be able to try to classify, is it an ionic compound? And we're kind of picturing those as metal, non-metal pairs that are ionic compounds. And then we also have acids that we'll learn. And some of these types of compounds we've already seen before. So let's give a couple examples just to kind of see some things that we've probably already had examples with in the past. Like we know NaCl is sodium chloride, and that's an ionic compound because it's comprised of the sodium cation, the chloride anion. We might remember things like sodium sulfate, which is Na2SO4. We'll systematically learn how to name compounds like sodium sulfate here in chapter 2, but that's just going to be called sodium sulfate. We'll see the compounds like calcium chloride is CaCl2, and one of the kind of key details here is kind of starting to pick up that certain ions have charges, and then some of those charges we can determine from periodic table placement. Other charges we're going to have to learn just by example and by basically memorization, or through having seen these things before. Like you may have seen SO4 with a 2- charge before. That's the sulfate anion. It happens to have 4 oxygens attached to a sulfur with a 2- charge. That's what we call a molecular ion. So we have some atoms linked by covalent bonds with an overall charge. It gets a little bit into the weeds to kind of start to draw the structures, because I don't want you to get confused into thinking you're supposed to know or be able to sketch like a Lewis structure yet. But what sulfate kind of looks like is something kind of like this. And then there's like 2+ charge on sulfur. We'll talk about why that is in chapter 8 and 9. But I just want to give you a sense that anytime you see a collection of atoms like SO4 2-, those are going to have some type of covalent bond linking those atoms together, like single or double or triple bonds. And we'll talk about the nature of that bonding later in the class. So you won't be expected to necessarily interpret or sketch a Lewis structure, but you can sort of start to picture, okay, like I can kind of grasp that for some reason sulfur can grab a hold of some oxygen atoms, have a charge, and that's a commonly found anion. We find sulfate in minerals, we find it in nature, we find it in our bodies, so it's an important anion that we'll learn how to name in this chapter. We have encountered acids. I'm sure you've seen like things or seen the names or heard the names like nitric acid. Nitric acid is HNO3. Most of you guys probably knew that, or probably when I said that, you're probably like, okay, yeah, I remember that being like a formula I've seen before. That's nitric acid. You may remember like hydrochloric acid is HCl. So we've encountered some acids before, maybe in high school examples, you've seen these. I just want to cue us in that an acid, what it's going to do, and we'll learn more about this in chapter 4, then you'll learn more about this also in chapters 16 and 17 in Chem 1220, is that acids release ions, the H+ ion, into water. And that's what makes something really behave like an acid. So we'll kind of try to introduce that a little bit when we get to a slide naming acids later, and then a little bit more in chapter 4 when we start talking about things that go on in water. So acids are things that have like H+ ion. So recognition of an acid we'll see is like seeing like kind of like an H+ ion and then some underlying ion we've learned how to name. But these actually turn out not to be ionic compounds. Like Na+ has a positive charge, chlorine has a negative charge. HCl is really a molecule that exists with that covalent bond. And there's a lot of interesting details we'll also pick up in chapter 8 and 9 on bonding and how it's a polar bond. You may have seen this before, but again, we'll come back to examples of talking about molecules that look like things like HCl as we progress through the course. In this chapter, we're just going to try to get the idea of what's the formula, what's a name I attach to it, and then what's the kind of category of compound it fits into. And then other categories of compounds we'll name are things like alkanes, simple hydrocarbons. We've seen these before, methane, ethane, etc., are two compounds that are hydrocarbons. So we'll try to pick up a nomenclature system so we can get the formula names for those compounds. Alcohols are where we replace a hydrogen off one of those compounds with the hydroxyl group, the IO group. So the hydroxyl group are alcohols. And so C2H5OH is the formula for ethanol. So alcohols are similar to alkanes, just where we replaced one of the hydrogens with that hydroxyl group. And so we'll try to pick up a systematic nomenclature system, and you probably can already kind of see the nomenclature system, how we go from methanol to ethanol. You may have already known those names, and those are the systematic names for those molecules. And then we'll learn how to name binary molecular compounds, and so there's a lot there, but molecular compounds are non-metallic elements. And then binary just means two. So it's having two non-metallic elements present within the formula. So two examples would be CO and then CO2. So a binary is having two elements present, but in any proportion. So we could have, something like NO, we can have N2O, we can have N2O5. Now, not every connection, not every set of numbers I might write is a real molecule that can truly exist. But, can we name what the formula's name would be if it did exist? Or generally speaking, if I give you a formula example, it's going to be something that actually exists. Like for example, carbon really only forms the stable compounds with one oxygen with two oxygens. So I'm probably not going to give you an example of like C2O6 to name or something like that, because that's not really a molecule that forms between carbon and oxygen. But carbon and oxygen form two really common compounds that we see a lot in nature. One of those is carbon monoxide, that's this one, and the other one's carbon dioxide. And I just want to start with the CO examples and the CO2 examples because you probably knew CO was, did anybody not know CO was carbon monoxide? Is anybody seeing that for the first time? Probably not. But the key is that the name carbon monoxide is the true systematic name. So a lot of the names we know from these formulas we've seen before and the names we might already know or have seen are the true systematic names that we can build from those and kind of pick up the system as we go along. I guess I thought this was the next slide. But this is the lecture quiz for anybody who's come in over the last couple minutes that needs to do the quiz. And again, if you missed this link, the key is that it's going to close in about 4 minutes. So it's set to close at 8:10 this morning. So these quizzes will roughly either close at the end of class if we do the quiz at the end of class, or it'll close roughly about 10 minutes after we give you the link. The key word here for today is density. So if you come in, you may ask, if you come in late, you may go to your neighbor, has he done the quiz yet? And if they say, yeah, you may say, what's the key word? That's fine if you guys share the key word if somebody does come in a couple minutes late. Okay, so with that again, keyword today, density. You can always get to the quiz without the link just by going to Carmen. And then, so I'm going to move off the slide now. Okay, so I just wanted to start, and again, I think we've already passed for the quiz today. But so I think it's already timed out. But anyways, let's move on to ions, ionic compounds. Kind of globally to think about them first, let's think about the nomenclature system for these types of compounds. And so ionic compounds, we're talking about form between things like sodium and chlorine, where sodium should have 11 electrons, like elemental sodium, according to the periodic table, 11 protons would have 11 electrons if it's neutral, but if it loses one of those electrons, it goes and obtains a positive charge. So it lost an electron, now only has 10, and then chlorine takes that electron that was lost, so it picks up 18 electrons. So the electron goes over to the chlorine atom to form the Cl-. So we didn't lose any electrons or gain any electrons net between the two elements, we just exchanged them. We just took one electron off sodium, put it onto the chlorine atom. And so we've now formed sodium with a positive charge, chlorine with a negative charge. And then once that happens, they have an electrostatic attraction with each other. And then the other thing that happens is you take the negative and the positive, they then link up with another sodium and chlorine that did the exact same thing. And you start having this alternating negative chlorine, positive sodium, negative chlorine, positive sodium, and you end up with a crystal. So you end up with a crystal lattice where you have in all three dimensions the alternating positive and negative charge. So if we had a jar or a single crystal of sodium chloride, we'd have millions upon millions of ions, all of alternating charge, all linked together by that electrostatic force of attraction. So when we think of sodium chloride, we have really just one compound that forms between those two elements. So when I look at sodium and chloride, unlike the carbon monoxide, carbon dioxide story where we could get two different compounds, nitrogen and oxygen forms all kinds of compounds. There's probably 10 different ratios of N versus O that form stable molecules together. With sodium and chlorine, there's just one. The only formula you get between sodium and chlorine is either NaCl or Na a million, chlorine a million. You just get all these ions linked together. So the formula that we write for ionic compounds is the empirical formula. The simplest ratio of the ions. So we look at the ions in the compound, sodium and chlorine. They both have a positive and a negative charge. And so, of course, it's going to be sodium 1, chlorine 1, or just NaCl is the formula for that ion. And like, we're not going to get Na2Cl. We're not going to get NaCl2. We're not going to get NaCl4, any of these other combinations. The only combination we can get are these two here. Now, it's a really loaded question in terms of, well, why do you not get sodium plus 2, chlorine minus 2 ever? And the answer is that it would take too much energy to kick another electron off of sodium to go to plus 2, and we wouldn't get back enough energy if we put that extra electron onto chlorine. So it never does it between these two ions. Now, we'll see some examples as we continue. Let me do one thing, since in my head I'm still feeling bad that anybody who just came in over the last minute can't do the quiz. Let me change something real quick here. So if you had just come in, you should be able to do the quiz now. I just bumped the due time out. But the keyword today is density. So just go to Carmen, navigate to the quiz if you need to get today's attendance points. So the keyword again today, density, capital D. Okay, so back to ionic compounds. The simplest ratio of the ions is how we express the formula because that's the only compound possible that we could obtain. Like if we go to calcium and chlorine, calcium is just in a different position in the periodic table. We were talking last time on how calcium's position is it can lose 2 electrons to obtain that especially stable configuration. So it's going to go to a 2+, chlorine going to a minus. So this compound can only form where we have 2 of these minuses to counterbalance the charge. Because the formula needs to be charge neutral. Now, why would a molecule need to be charge neutral? That's another loaded question. Well, if we had a sample that had a net charge, if we had a sample where all of the ions somehow configured in such a way that there was a net charge on the molecule, if we had like CaCl, where there was like a net positive charge, it was just a +1 compound, there'd be such a positive charge, you'd just be looking for a negative charge to balance it. That's what you call like a thunderstorm. That's what you call a lightning strike. That's just a reaction waiting to blow up that's just never going to form. So if we have a bottle of something, it has to be charge neutral. If we had a bottle that had a net charge, it's just like looking to get the charge to balance it from somewhere, and it's going to do so well before you could ship that chemical across the country, if that makes some sense. So compounds have to be overall charge neutral. So that's why we would have 2 chloride ions, -1 each. And the chlorine, again, it's based on the position, but just picking up 1 electron to go to that stable count like argon's count of 18 electrons. Okay, so calcium chloride would form the CaCl2 formula, and that'd be the only compound that can form between those 2 elements. So reminding ourselves of a few charges we had gone over last time, we look at this chart here. Our alkalis are all +1s. Go to the laser pointer. Our alkalins are all +2s. Our aluminum was our primary example, that's a +3. And the reason why you don't see boron above it included or some of the elements below is because they start to have a variety of properties where they don't exactly form ions in the same way that aluminum does. So aluminum's the best example in its in its column that forms an ion in this sort of fashion here. Boron does some interesting chemistry, has interesting formulas that we talk more about later in chapters 8 and 9. So let's come back to boron then. But then in terms of hydrogen, it can either be +1 or -1 depending on the partner it pairs up with. And then the other halogens -1, the oxygen group all -2, and then the nitrogen being the primary example, that's a -3 ion. And then all the other ones just don't really, like carbon doesn't really form a 4- ion commonly enough to name it. And so these are the commonly formed ions that we call monoatomic ions or simple atomic ions, just 1 atom, 1 ion of the indicated charge. And then all of these names here would just be, on the positive side, lithium ion, sodium ion, potassium ion, or magnesium ion. So it's just the element name followed by ion. And then all the anion names take the IDE suffix. They just kick off the ending on the element and change it to "ide." So for example, oxygen becomes oxide. And we don't trick you, is it like oxygenide, is it oxygenide, is it oxide? It just turns out it's oxide. Nitride is the nitrogen one. So where do you cut the root name off in the element varies a little bit. Like sulfide is the S2-, so that becomes sulfide. But we don't try to trick you on like where do you cut the element name off and add the IDE suffix. So if you see IDE ending in, if you see a word ending in "ide", you know it should be a simple atomic ion of one of these elements here, and you just kind of look for the root name to figure out, okay, it's sulfur, iodide for iodine, bromide, chloride, fluoride. One last one to point out, though, would be the H- ion is hydride, which makes sense, hydrogen to hydride for that simple minus. So we see the IDE ending, that tells us that we have a anion, and that simple variety of anion. We'll see some 8s and ites in a little bit. 8s and ites are going to tell us that we have some other type of anion. So we'll have to learn what kind of category those fit into in a moment. Now, what about all of these elements here? What about our transition metals? It turns out that they form a lot of different cations. They often will form multiple different cations. So for example, iron is the 6th across. So iron is here. So that's iron. And then iron most commonly forms the +2 or the +3. And so for iron, we're going to have to come up with a systematic way to name iron so that we can know, is it the +2 iron or is it the +3 iron? And then also notice that neither one of those happens to be the one where we lost all of the electrons to get towards that noble gas configuration. So our transition metals are going to form a variety of charge states. Sometimes they'll lose all of their possible electrons to go to that sort of noble gas configuration, but sometimes they'll stop somewhere in between, like iron 2+ and iron 3+. And so the way we'll name these, I think this is on a slide in a moment, would be just to use a Roman numeral. So iron 2 is iron 2+, and then iron 3+ is Fe. So Fe3+ is iron 3. So we just use a Roman numeral indicate what the charge is. And then we do this for the transition metals. And we'll even do it for things like lead is right there. That's tin. But we'll do it for like things like lead and tin and some other molecules that are kind of in the the box area that don't have an element symboled in this chart. So the symbol using the Roman numeral is helpful because it tells you the charge. It tells you what the charge of the ion is right off the bat. So we'll pick up that system as we continue here. So let's summarize a few things. So the things that are kind of like conventionally named are in red, just where, by convention, alkalis are +1. That's the convention with alkalis, that they're +1, and the alkalins are +2. And remember, alkali, alkaline are easy to mix up, but the alkalis is the first group of elements, and the alkalins the second group. If I say alkaline, sometimes it sounds like alkali. So depending on how you say the words, you may confuse them, or just make sure that when you see alkaline, you might think alkaline, just to make sure you see as a different word than alkali. And the alkaline are the second group, they're +2s. Aluminum's at +3. Now we have a couple of formulas that will come up in examples that we may just have to kind of recognize by formula. That would be like ammonium is NH4+. You might remember, or you might have seen NH3 as ammonia. And so the IUM suffix is really common on things that are either positively charged or likely to form cations. That's why most of your metals end in IUM in terms of their suffix, because they're tending to form positive cations. In fact, our left side elements, the black shaded elements on the chart, well, actually, those aren't just the metals. The metals on the periodic table, if we had a different periodic table that indicated the metals versus the non-metals, metals only go positive. You're not going to see sodium go negative. You're not going to see iron ever go negative in charge. Metals are always positive in their charge state when they form ions. And then the non-metals tend to be anions, with hydrogen being that one example that sometimes is positive. And we'll see a few details later in chapter 4 about non-metallic charges. Another thing that comes up more later, not so much in this chapter, is H3O+. We call that hydronium. This is more of a concept for like chapter 4 or later chapters on equilibrium involving acids. But H3O+ is like a protonated water. A proton, let's talk about that real quick, because I just said a word that maybe doesn't make sense. Hydrogen has 1 proton, and the most abundant form of hydrogen has 0 neutrons. So the hydrogen atom, the nucleus of the atom is just 1 proton. And so an H with a plus charge, we often just call that a proton, because that's, in simple form, that's all it is. So if you add an extra proton, so protonated water, H plus added on to water is H3O+, that's hydronium. And so again, H plus only contains 1 proton as its subatomic particle. No electrons, no neutrons. And so in terms of symbols, we'd have that 1 up here, and then the atomic number 1 for hydrogen. So transition metals, we name those with the Roman numeral system. So you'll pick up and see like copper 2s, copper 2+, manganese 5 would be Mn 5+. And then also remember magnesium is the Mg. So manganese versus magnesium, sometimes we get the element symbols confused. Make sure that at least for the first 4 rows and some of those important groups like the alkali, alkaline, halogens, noble gases, that name to symbol, symbol to name doesn't trip you up. Again, you don't need to memorize placement of the elements, just the name to symbol, symbol to name pairs. These are a few things that sometimes historically come up in examples. Like if you look at some practice quizzes, there's a few transition metals that will actually only form 1 charge state that might be worth knowing. Zinc only forms a +2. We often call that the zinc ion without using a Roman numeral. I prefer that we do, but sometimes you might see like zinc chloride and have to interpret that zinc 2+, so I just wanted to point that out. Silver only ever forms the silver plus, and it's common enough that we tend to just call silver ion silver plus without using the Roman numeral 1. So you might see a lot of examples that say silver nitrate or silver chloride without the Roman numeral 1. So I just wanted to point out silver only forms this 1 ion, so you may see examples that lack the 1 symbol for silver, even though it's periodic. Even though it's in that transition metal group of elements. Lead is in this group too. We tend to, sometimes we'll call it lead 2 chloride, but a lot of times we'll also just say lead chloride, and we're interpreting there lead can only form a 2+, so if it forms a compound with chloride, it would be PbCl2. And then mercury does something interesting that we'll point out and use some examples and see some examples in chapter 4 of. It forms a weird mercury 1 compound where like 2 mercuries bond together with a net positive charge on either side. That, in terms of formula, is Hg2 with the 2+. If you notice, that kind of looks like, on average, it's a mercury with a plus charge. And so we call that mercury 1. So that's a systematic name. I doubt you'll see it on naming. You might see it in a few naming examples on my quizzes because we used to name this for exams, but you probably won't see it on an actual exam this semester. So you may see some examples of that. I like to point it out here because we'll see that ion in chapter 4, and we really have to differentiate it from its sort of partner mercury 2, Hg with the 2+ charge. That's just the ordinary mercury 2 ion that conventionally you would think mercury 2, Hg with a net 2+ charge. And so I just want to highlight here that mercury 1 is not Hg+. That might be what you think mercury 1 is, but it really is mercury 2 of them with a net 2+ charge. But then mercury can also form the very ordinary Hg 2+. Now, what does this mean? Well, it means if you pair this up with chloride, we go Hg2Cl2 for mercury 1 chloride. And then if you have mercury 2 with chloride, it'd be HgCl2. So in other words, for mercury, you get two different compounds. You get mercury 2 chloride, mercury 1 chloride. Mercury 1 chloride looks a little bit weird because you get a formula that looks like we should have divided both the 2's by 1. Remember how I said on a prior slide that we write the empirical formula for ionic compounds? It's the empirical formula of the underlying ions, if that makes sense. It's the simplest ratio of the ions. And the simplest ion is Hg2, 2+, so I can't break that down in terms of the formula. We'll see other examples of that as we go along. It's kind of like hydrogen peroxide. Does anybody know the formula of hydrogen peroxide? Somebody knows it, H2O2. Yeah, and it's like the joke. Like I went to the bar and my buddy ordered an H2O, and then I ordered an H2O2, and I died. Anybody ever heard that joke? It's a dumb dad joke because the first guy gets water and the second guy gets hydrogen peroxide. But hydrogen peroxide, H2O2, we write that as a formula, not HO. So it's important for hydrogen peroxide to kind of express the formula of that molecule. Important to express the ratio of these actual ions here as Hg2Cl2. What I like to mention here, just to kind of understand why I'm talking about mercury so much, mercury 1 does something in chapter 4 that mercury 2 doesn't do, and we have to differentiate those properties. And I don't want you in chapter 4 seeing that for the first time. So we'll come back to mercury examples, and we'll see some examples of those later in the course. Okay, so we have polyatomic cations, just like we did anions. We were talking about sulfate on that opening example where we just have central sulfur, the other oxygens connected to it. Ammonium, same basic idea. We have hydrogens attached to nitrogen. They have some three-dimensional shape that's not attempted to be indicated here. So if you start thinking of what does this thing really look like, we got to get deeper into this. We'll come back to that later in the course. But I just want you to see that the idea is that these are molecular anions. And so we have a polyatomic cation, NH4+. We have those covalent bonds linking the atoms, and we just then have a overall positive charge for ammonia. It happens to lie mostly on the nitrogen atom, but again, not a big detail to memorize or know, but just that somewhere in this molecule there's a positive charge, and then on sulfate we have the collection of atoms with the overall negative charge. Let's learn these 8s and ites and get into that discussion. And so let's look at some oxyanions. So oxyanions are where we have a sort of an element that has oxygen attached to it and then overall a negative charge. And so if we look at an example of that, might be carbonate, where we have the central carbon. Turns out in nature, like this is really where you go to nature and try to say, well, for carbon, what do we find? Most predominantly with carbon, the most commonly found anion is carbon with 3 oxygens and a 2- overall charge. And so that takes the ATE ending. So the most common oxyanion of a given element with the indicated number of oxygens and the indicated number of charge is that ATE ending anion. And so carbonate is what we call CO3 2-. Nitrate, the most common one, is a 3 for the oxygen count, but only a - for the charge. And so that's nitrate. And again, we're not trying to understand why this is the formula. Why is this nitrate and not some other count of O's and some different charge? Just we're trying to see that, well, we're going to memorize 3 oxygens with a - is nitrate. But if I take phosphorus, it's going to be 4 oxygens with a 3-, so that's phosphate. So the root name of that element followed by the ATE suffix. So sulfate, so sulfur, 4 oxygens with a 2- charge is the most commonly found oxyanion of sulfur in nature. And then for chlorine, it's like nitrate, it's 3 oxygens and a - charge. So we could memorize this. Like this is like the one thing that if you haven't seen these and you don't know these formulas and you haven't seen them ever before, or it's been a while, just make flashcards of these. This is something worth making a flashcard of just because there's no other way around it. We just have to kind of memorize 3 oxygens with a 2- charge for carbon, et cetera, down the row. Now, has anybody ever heard that phrase there, that Nick the Camel ate a clam supper in Phoenix? Has anybody ever seen that before? Do you guys remember what it means? So, like Nick is for nitrogen, and the consonants are the oxygen counts, and the vowels the charge. Somebody told me this once in office hours like 10 years ago, and I remember thinking, I think it's going to be harder to remember Nick the Camel ate a clam supper, and to even remember that the camel is the carbonate and the clam is the chlorate. But it seems to me to be harder to remember the phrase than the actual fact that, nitrate is the 3 and the minus, and the carbonate is the 3 and the 2 minus, and the phosphorus is the 4. Phoenix, 4 consonants, 3 vowels. So you can either remember how to spell Phoenix if you need to pull this out for like a test, or you can just flashcard phosphates the PO4 with a 3- charge. So I just want to mention that there's a mnemonic you can try to memorize and use, or just memorize or flashcard. But this is not a whole lot of things I think you need a flashcard in this class, but nomenclature, of course, is going to be one of those topics that making a couple flashcards. Oh, guess what? You can use AI to make flashcards. So you can have AI create flashcards of nomenclature for you. Just tell it what the chapter is and what textbook you're using, and I bet it comes up with a pretty good nomenclature set of flashcards for you. Okay, this is another summary slide, but this one here is showing us that for the second row, period 2, that we either have a count of 3 for the oxygens, and we can't go to 4. So you're not going to find in the second row any examples where we kick and have 4 oxygens in any kind of formula. So for the second row, the maximum number of oxygens is 3, and then the third row, we can go up to 4. So we'll see that for phosphate and sulfate, they already start with 4 O's, and chlorine, we can actually add an extra O to the formula to go to ClO4-. We just have to figure out how to name that, and we end up naming it perchlorate. So let's talk about that nomenclature system. So if we take an anion, any of them here, kind of start with your representative oxyanion, one of those 5 from the previous page. We'll start with the example here of chlorate. And then if you add an oxygen to the formula, that's where the per comes from. So we go to per chlorate when we just add an O to the formula. Now, you can have a lot of questions. You could be saying, well, how did you add an O? I have no idea how this thing added an O. Somewhere in nature it finds an oxygen atom and it keeps the same charge. And so we just changed the formula to ClO4, keeping that minus charge intact, not changing the charge, just literally changing the oxygen count. And then we just kick on the prefix of per. So perchlorate, ClO4-. And if we take an O away, and another thought is that we actually do see these formulas in nature just a little bit less often than the chlorate example. So the chlorate's the one that we see the most in nature, and these other ones maybe not as much, but they're still observed. So ClO2-, we just then go to the ite. So we change the ate to ite to indicate that we have chlorite. And then we go to hypo out in front when we kick a second O off the formula to go to hypochlorite with just 1 oxygen. And now even hypochlorite, you might look at that and say, well, that seems strange. Why would anything exist that looks like that? Well, that's the common ingredient in bleach, is like sodium hypochlorite. So this is actually a very, very useful and readily used compound in everyday life. So this is something that you can find. So NaClO, that's what you find in bleach. So that would be sodium hypochlorite. Okay, so now the other part that comes into to kind of challenge or question is, well, what about like nitrate and carbonate? Do we have to know the full range here? But remember, I just said that like the second row, nitrate, carbonate in the second row, they really can't go to 4. So you're never going to see a per nitrate or per carbonate example because they don't exist. So we're gonna try to not give you examples of molecules that aren't things that really exist. So we're gonna try to limit the examples to the things that exist. We're not gonna try to ask you, does this exist, does this not exist? That's really not a great question in my opinion. We're just trying to really get a system down for, if you see a formula, can you tell me it's an ionic compound because it's in this category, and then can you name it? If I give you the name, can you write the formula? That's really the goal of this unit, is just name the formula to name. this slide here will kind of take you through the range that we tend to see in nature and kind of the limit of the examples that you'll see. So I think another slide later might show this on it. I just wanted to make sure, sorry, it'd be CO2, 2 minus. I think this is on a summary slide in a moment. So let me go ahead and jot this down here, that this would be carbonite. Just in case it's on that slide a couple slides from now, so you can see that it didn't come out of nowhere. But CO2, 2 minus, if it were to exist, we're just changing the ate to ite. So anytime you just lose an O, you just change the ATE ending to ite. So if you go from 3 to 2 for nitrogen, nitrate to nitrite. So sodium nitrite, NaNO2, truly exists. Sodium nitrate, NaNO3. Different formulas, different names, different molecules, different compounds. Phosphate to phosphite. So notice for most of the compounds, we're not even losing the second O. So most of the examples are only just the ate and the ite. And it's really only with the chlorine example that you go the full range of ite to hypoite and then all the way to per. Now, if we told you that like bromate, for example, is BrO3 minus, so let's say on a test we tell you this, then we could say, well, what would the formula of what would this be named given that detail? So you'll see some examples that are like, well, if this is that, then use the system to conventionally name this other thing. So you'll see a few examples that may say, well, if you know bromate is just BrO3 minus like chlorate is, then what's KBrO4? And this is potassium perbromate. So you can kind of conventionally name some things if you're given some information. Let's look at oxygen for a minute. So we know from the previous page that oxide is the atomic ion, just the simple simple anion named oxide. Now, what do you think we would call O2 with a 2 minus charge? I've already mentioned it today, so you probably have the name in your head already. But just think conventionally now. When we add an O, you just put the per out in front. So that's actually where the name peroxide came from. So the name peroxide actually fits into this system where if you add an O to the formula, you just put the per out in front. And so peroxide is just the O2, 2 minus. And so now in terms of the O2, 2 minus ion, you could pair that up with something. Like you could pair that up with potassium. So if you have potassium peroxide, you just need 2 of the K pluses. So K2O2 would be potassium peroxide. And now, do you see in this example here, we wouldn't want to call this KO. We don't simplify it down because the simplest anion that we can write, the simplest formula for peroxide is O2, 2 minus. We don't call it O minus and break that down further. So this would be the formula for potassium peroxide. Now, potassium oxide would be the ordinary oxide ion. So we can have a different formula between K and O that we would call potassium oxide. So that's just potassium oxide. Potassium peroxide below. Now, let's do a couple formulas here, and we'll throw a bunch of examples in here, but calcium nitrate, what's the formula there? What do you guys think? So I use parentheses, so I'm going to need more than one of a molecular ion or a collection of atoms that have a charge. So if I have minus, I need there to be 2, right? So I need this to be CaNO3 too. And then when I do this, what I'm usually trying to do here is just to show that the charges aren't part of the name. That the charges, the charges aren't part of the formula. So when I write the formula, I usually don't include the charges. I need to think of the charges to get the proper subscripts. But I lasso the sort of formula out to neglect the charges when I express the formula. What's the name of this guy here? You can also verify that the charges make sense too, right? Because we can remember that calcium's only a +2, phosphate's not a plus, phosphate's obviously a minus, it's a -3. And you see how the math works? We have a total of +6 from the calciums, a total of -6 from phosphate. So we have a charge neutral. Ionic compound should be charge neutral overall. This one is. So what's the name here? Calcium phosphate. Now, luckily, most of our nomenclature is multiple choice. I don't think we do anything that you have to type in the name like on a test. So you're looking for the name that makes sense based on a list and multiple choices. So let's look at a couple other anions that we name kind of more conventionally. There we go. So the OH minus ion is what we call hydroxide ion. So this is just an ion that we'll see a bunch in examples and just have to kind of systematically learn that it's just conventionally named as hydroxide ion. And so the calcium hydroxide, what would its formula be? So calcium 2 plus, and then OH with the minus. So we're going to have 2 hydroxide ions. So CaOH2. Acetate ion comes up a lot. We may have known what acetic acid is. I don't know if you guys have ever seen that before, but you might know, and this will kind of clue us into acids a little bit later, that acetic acid looks like this. We could also write the formula a different way. So sometimes you see acetic acid written as HC2H3O2. This ion here, or this ion here with the negative charge, is the acetate ion. So we can write acetate one of 2 ways. And one way is more descriptively the order that the actual bonding goes in the molecule. That will make more sense when we see that later, if you've already seen that before. We just get a CH3 group and then the sort of carboxylic acid group. But you'll see that later in chapters 8 and 9. So I think later this way will make more sense. Or if you've already seen it, that might make more sense. But for now, I think this formula, the C2H3, kind of condensing the formula makes a little bit more sense now. So I like to use this formula a little bit more here in chapter 2. We'll see the other formula a little bit more later. But then we also get the K plus out in front, so the sort of metal, non-metal pair. So whenever we see metals mixed with non-metallic elements, we know we have an ionic compound. And so this would be potassium acetate. Now, something I haven't stressed, just to make sure I stress here, that the 2 in the hydroxide doesn't go into the name. Like calcium hydroxide wasn't calcium dihydroxide. Calcium chloride wasn't calcium dichloride. So just make sure that we're always naming the cation name followed by the anion name, and we don't need to indicate anything about the ratios of those ions because we pick those up from our nomenclature and our systematic understanding of their charges for what they have to be. Like calcium's only charges +2, hydroxide's only charges minus, so calcium hydroxide has to be CaOH2. Okay, and so we already were going over and talking about the peroxides, but calcium peroxide, I won't write it, but that's calcium peroxide. And then the superoxide ion is an interesting one. The superoxide is where we have the O2 now with only a minus charge instead of even the -2 charge. And so that's yet another ion of oxygen that forms. And so that's the superoxide ion. So if you see KO2, the thing you can know here is K has a positive charge, can only be a +1. The O2 here, therefore, must be interpreted to, as a group, have an overall minus charge. And so that would be potassium superoxide. You probably won't see too much about peroxides or superoxides on exams, but I just want you to know that this exists. You'll see them, examples with them later in other units, though. An important distinction is that these peroxides and superoxides are only forming with alkali metals for superoxides, only with alkali or alkaline ions for peroxides. So they're not forming with transition metals. And I just want to point that out so that if you see something like titanium with 2 oxygens, that the only possibility for oxygen here, if I'm breaking down this compound and trying to think, well, is this peroxide? Is this superoxide? What's the charge of O? It can only be -2O. It can only be the ordinary oxide. So I think oxide, most stable, most common. Peroxide, a little bit rare. Superoxide, even rarer. Superoxide is only with alkali. Not even sure you need to memorize that detail, but just that you're only going to see it with a metal that you know the charge of. This same thing with the peroxides. You're only ever going to find an example of a peroxide where you can look at the metal and know it's a +1 or a +2 based on it being an alkali or alkaline metal. But with titanium, it's a transition metal. I don't know its charge right off the bat, but I do know that it's a -2 times 2 for a -4, so I can deduce that the charge of titanium is +4. And so this would be titanium 4 oxide. And so the other detail with the Roman numeral system with transition metals is I can then break down what the Roman numeral has to be based on the idea and concept of charge. So for example, if I see a compound that's like, say, Cu3PO4 2, how do I name this thing? I have to like deduce what the charge has to be on copper to make those ratios of those ions come out to be the right ratios. So how do I do that if I'm naming this thing? Well, remember that phosphate has to be a 3-. There's 2 of them, so there's a total of -6 coming from the 2 phosphate groups. So I have to have a total of +6 from the 3 coppers. So what does that make the charge of each copper? +2. And so it makes this +2. You could have also been thinking, well, what if I just take the 2 to here, the 3 to there? You can do some cross math, thoughts to get those charges too. But the charge of copper +2, and then the charge of phosphate -3. So what would the name of this compound be? Copper 2 phosphate. All right, so here's a summary of the anions, and I don't know why I'm getting this lag again today. Must be OSU Wi-Fi. Is your guys' Wi-Fi struggling today? This is probably what it is. Yesterday I was having issues. I don't know if you guys were too, but yesterday afternoon I was like, nothing was loading. It was like, how have we not figured out Wi-Fi with like 60,000 students on campus? This isn't new. Okay, so again, some summaries and some reminders. The things in red are things we just pick up by convention. So hydrogen, simple ion is a minus. If you think of hydrogen, it can lose 1 to go to no electrons, or can gain 1 to go to the helium count. That's kind of why hydrogen kind of can go either way here. H- is the hydride ion. The halides are the minus charge ions because they go to that stable noble gas count. So fluoride, chloride, bromide, iodide. Oxide, sulfide are the most common examples. I've left the other like selenide and tellurium, telluride. We don't see too many examples with those bigger elements. So these are our primary examples that we'll see here for oxide, sulfide. Nitride, I guess I threw phosphide here. You might see phosphide every now and then. It doesn't really form 3- very commonly, but it's in that nitrogen group of elements. And then hydroxide, acetate, and then here's our carbonate, nitrate, phosphate, sulfite. Like this is what you probably want to know is the nitrate, phosphate, sulfate, chlorate, carbonate. I guess carbonite wasn't on this list after all. I thought carbonite was on this page, so I guess you really don't need to know too much about the carbonite. But again, it's not so much about memorizing all these details. It's just like being able to see the element or the collection of atoms and be able to name it, and that this is just kind of the range of things that you're going to see examples of. So I hope you see that it's not necessarily like the longest memorization list, but it's like some conventions, some things we can memorize, and then some other things we can name based on the conventions. And so then some other things that, again, that we mentioned likely probably don't appear on tests that often that you may see examples of. So peroxide, superoxide. Cyanide is important because it's toxic. Like you don't want to encounter cyanides, are like commonly found in like rat poisons and things. So it's worth knowing and seeing that cyanide exists. But Cn- is a cyanide ion. Like we mentioned, bromate. Iodate is the version like chlorate and bromate, IO3-. Oxalates and Ts and things like that. So you'll see examples of like oxalate. It's in a molecule you'll see in OChem if you take that class, but that's the C2O42- ion. So those are some other ions you may see formulas of that we don't really expect that you have memorized for exams. So with that, let's look at the sig fig problem. It's kind of like a good kind of chance to take a step back and kind of go back to something from chapter 1. So let's do this together here. And like, again, when we multiply, we do the multiplication rule. And the multiplication rule is the easy one. That multiplication has to only have 2 sig figs, because I have 2 sig figs times 3. So I go 0.00015 times 54.6. So that result is 0.00819. Now, if I were reporting that result, I'd call it 0.0082. But I'm going to leave the 819. It probably isn't that big of a detail to include the extra 9, but I'm not going to necessarily round yet. I'm going to try to wait till the end of the problem. Then I'm going to do the addition step. And so I just have to carefully line my numbers up and then round accordingly. So I'm going to round this to 1.010 with 4 sig figs. Okay, so I just then apply the addition rule. I look for the greater quantity placeholder. So it's either the thousands place or the 10,000s place. So I round to the greater quantity placeholder, that thousands placeholder. Let me get a sense of what's to come here. So the next category of compounds we name are acids. And really recognizing acids becomes the first part. And I can recognize an acid if I take any anion I learn how to name and just like neutralize the charge with H pluses. So if we can just picture like chloride, neutralize it, it takes 1 H plus. So HCl is that acid. But the confusing part is it's no longer ionic. Like it seemed ionic when I put those units together to make the molecule, but once I connect those atoms, they form a bond together and stay stuck together. If I do this with chlorate, again, it takes 1 H plus. If I do this with sulfate, it's going to take 2 H pluses to balance it out. But then once we do that, it forms a molecular compound. So all these compounds here are molecular compounds. Molecular compounds charge neutral, different in behavior from ionic compounds. So let's end on that. Ionic, metal, non-metal. Whenever I see all non-metallic elements, even if it seems to be something that could form an ion, possibly, I still call it a molecular compound. We name it as being an acid. So acids are these neutral molecules that have, underlying anions we can recognize that we name as this category of compounds as being acidic or acids. All right, so we'll stop there for today. I'll see you guys on Friday. Have a great day.